So yes, I'm going to show you an interesting feature in the double white dwarf separation distribution that I believe is very interesting from the theoretical perspective to constrain our models. And this is a work that I've done in collaboration with Silvia Tonen and Valeriya Korol. So Nama has already mentioned a little bit the motivation to look at the double white dwarf properties as a population, and even if we know quite a sizable sample of resolved systems, our current knowledge is still incomplete, and that's simply because, we are because of the selection effects of the methods that we are using for discovering them, we are biased to orbital periods less than 1 day. And now with the upcoming Gaia astrometry, maybe we are going to fill in a little bit more this part of the diagram. However, the region in between will remain difficult for both methods of the spectroscopy that is more used over here and astrometry. So still we can look, we can access this region if we look at unresolved Gaia binaries via the astrometric wobble. So let me explain you the concept. So I'm sure you know very well how the motion of a single star looks on the sky, and it is something like the black curve over here. However, if our star is actually an unresolved binary in which the two components have different intrinsic luminosities, then what Gaia is going to see is the common motion of light rather than common motion of mass. And that's the red curve in this example. So what Gaia samples is the common motion of light, because we are looking at photometry. And if we are going to feed these data points with a single star astrometric solution of 5 parameters, not 2 for the position, 2 for proper motion, and 1 for parallax, we are going to get a bad feed. And this is what we are looking at. So the working premise behind this project was to use the amplitude of the photocenter perturbation due to the binary orbital motion that we can recover via the chi-square of the single source astrometric feed. And practically, we can do that by using the renormalized unit weight error, so the Ruve parameter that Gaia collaboration provides us, if we assume that it closely approximates the true chi-square. So we can test if this idea works just by color coding the Gaia HRD with the Ruve. And you can see immediately that the correct parts of the diagram light up in red with the high Ruve values. So the multiple, the most prominent regions, multiple stars above the main sequence, and the bridge between the white dwarf and main sequences. And now I can write down my chi-square formula, where here in the nominator I'll have my single source residuals, which is my fit-in model plus an extra perturbation that causing my bad fit. And I can solve this equation for the extra perturbation that I call delta theta. So this is the angular perturbation on the sky. And then I can translate it into the physical displacement, because Gaia also provides me the parallax. So this is how we get this quantity delta A, which is proportional to the binary orbital separation, times a factor that depends on the binary mass and light ratio, and I'll call it delta QL in the next slides. So this is our measurement procedure. For the rest of the talk, it's not going to be extremely relevant, so I'll highlight the most important details so that we can interpret the plots together. So first of all, we outline a box around the white dwarf sequence to select the candidates, and that's because, of course, we expect double white dwarfs to lie there or nearby. We look carefully how the parallax error behaves within our selected region, and then how it translates into the distances. Also looking at how RUVA behaves. So this is where the peak of the population, this is our background sources, and then how the outliers behave. But the most important detail is that we limit ourselves to look at the sources with the absolute magnitude between 8 and 13, and that's because this sample is complete up to a distance of 170 parsec. So this is the result. I'm showing you here the distribution of log delta A that we constructed via those few algebraical passages that I showed you before. And basically, you should look only on the black data points. So in this regime, we believe that our measurement is robust because as you go towards here, your astrometric wobble becomes comparable to the Gaia photometric error. And as we go towards here, then the binary orbital period becomes larger than the Gaia observation time. So we get, so the signal, detection signal shifts from the astrometric wobble to the proper motion anomaly. And this distribution can be fit very well with the broken power law. This is just a testimony that of what we get. And basically you have a shallow power law between -0.2 and -0.7 that steepens afterwards. Another important detail is that if you integrate this distribution, you get the total binary fraction in this separation regime, and we get 6.7 plus or minus 3.7%, which is consistent with other measurements. So before I showed you the delta A's that are not binary separations, but a proxy for this quantity. So we need theoretical models to be able to go to the physical separation. So here I'm showing you a few synthetic models for the double white dwarfs. This is the scaling factor that I showed you before that depends on the binary mass and light ratio. And this is the binary orbital separation. So I have two models here. One is the alpha common envelope that has been mentioned before, and another one is an alternative common envelope model that has been constructed based on the reconstruction of observed double white dwarfs. So here the total population is the solid line, and then the part of the population to which I apply all our selection criteria and cuts is in dashed. So basically, our scaling factor that goes to from delta A to A is close to 1. And if we go to binary orbital separations, we're looking at separations between hundreds and 1 AU. And in terms of orbital periods, that's between 1 and a few hundred days. So I got very excited about this especially because we get to trace very well this part of the distribution, and to explain you why, I have to show you the full evolution picture for these binaries. So when we start on the main sequence, say we start with the flat orbital separation distribution. As we look at the snapshot at the white dwarf main sequence stage, half of the distribution starts moving towards shorter separation. That's because one of the stars expands and it gets to interact with the secondary. And as we go to the double white dwarf stage, this distribution splits in two. So on the left, we have binaries that have interacted and specifically had experienced at least one common envelope, alpha common envelope. And on the right, we have binaries that have never experienced common envelope. So because the astrometric global data showing us the distribution. And as you can see, just by comparison of these two specific models, the width and the shape of the gap depends on the physics that we put in our models. So then I got a bit less excited when I compared my models with the data at face value. So again, this is the alpha common envelope and gamma common envelope model. And basically, we sort of doing well in at short orbital separation, but the model lack some binaries at wider orbital separations. And I ran a few model variations. I couldn't make up the match. So I actually don't know how to solve the mismatch at the moment. Of course, it is very well possible that the data are biased or there are contaminants, for instance, triple systems or white dwarfs with dark companions. And it's also possible that our prescriptions are not correct in this regime as well. So before jumping into say, changing all the binary population synthesis parameters, I did a few tests in which I allowed my distribution to move up and down, but also allow binary separation to scale. And basically, what I found is that if I allow my binaries to shrink less, so if I scale the separation by a factor of a few, depends on the model, then I get a very good match. And basically, one of the goals for me at this workshop was to discuss this with you guys. If you have any idea about what's going on, and especially if there is anything interesting in physics that we can work out here. So I can summarize, or I can just leave the slide. Okay, I think that we have an opportunity to learn.
Great. Thanks, Valeriya. Really nice work. I was wondering if you could do a similar exercise with the white dwarf M dwarf binaries?
Yeah, so actually we did, when we did a very thorough data sort of check and before coming up with the observed distribution, and we looked also at the mean sequence and white dwarfs, and of course you can do exactly the same process, but then the only thing that changes the scaling factor to go to the binary orbital separation. So for the white dwarf main sequence binaries, it's a bit higher. So you would look at the larger, the regime that you would be working in. It's a bit, it's like an order of magnitude towards larger orbital separation than for double white dwarfs.
But you also get the 1 day gap, or the gap by 1 day.
Well, that I don't know, because we have to reason on top.
Yeah, thanks. Karim was first? Okay. Yeah. Sorry.
Could you go back to the figure that shows the Roubaix across the CFD?
Mm-hmm.
Yeah. So it's true you can see there's excess above the main sequence in a white dwarf main sequence, but there's also a trend that as you go to faint sources, it just gets small because they're faint, and so you don't have any signal. So maybe I misunderstood how how you get the size out, but it seems like as your source gets faint, you just have a lower sensitivity to binaries. Is that right?
Yeah. Yeah, that's true. The brightness matters, but here you also have, like, the resolution of this plot is not high, right? When I select the white dwarf sequence, right, you really have those different rubrics mixed in within the.
Sorry, to just continue, if I may, can you go to the plot that has that looked like this? It was like that one, yeah. Exactly. So at the left side of this plot, basically you're in the regime of very little wobble.
Mm-hmm.
So how do you tell the difference between many double white dwarfs that have very small wobble, or just no companion at all? Like, aren't they give the same astrometric signal?
Well, yes. So that's another point, right? It's a little bit like what Nama showed with the radial velocities. We actually don't know. These are only double white dwarfs candidates, right? It would be like, I cannot be 100% certain that this is a double white dwarf binary. Like, ideally, I would have to follow this up to check.
Thanks.
Oh, nice talk. I'm just curious, within the parameter study that you've done so far, do you remember, like within the energy balance formalism for the common envelope, do most of your double white dwarfs undergo 1 or 2 common envelopes? And does that change with the model?
Right, it depends, okay, at the separation that we're looking at, or in general? In
the whole scheme of things.
Okay, so I don't remember the exact percentage in the whole scheme of things, because I work either at the shortest orbital periods or now over here. But here we are looking at here basically what we have is only one common envelope, and basically, so if I remember correctly, so this is the alpha model. So you have to have the first phase as a common envelope, and then a stable mass transfer to remain on this side, and that's the the leading channel over here. And as we add the gamma prescription in the model, then I have 2 of these as sort of competing channels, and this is actually why the gamma, which is blue, has more binaries than the alpha common envelope model.
Okay, thanks.
Hi. Can you go back to the plot showing the decrease in the ratio? Yeah, any of these.
One of these?
Yeah. What are the expected periods where the gap is?
Wait. So it's the gap, right? It is at 100 day or something like that. So here we are at 100 days.
Okay. I was just wondering, because Gaia ability to pick up binaries by astrometric wobble, so as the period approaches 1 year, Gaia, like the astrometric wobble, gets absorbed into the astrometric solution, and you get a sharp decrease.
Yeah, so actually, Nama kindly added this Gaia double white dwarf candidates that has been published as part of the DR3. However, I mean, the parameters that they publish are, are assumed ones, right? Because they are all at the same mass to solve for the astrometry.
They do show a sharp
gap
in at 1 year, because Gaia cannot detect them. But yeah, if it's 100 days, then that should be okay. Thanks.
Okay, I think it's time to move for coffee. So thank you, Valeriya. Thanks to all the speakers for a sec. We will be back at 4.